We're now moving into chemical bonding. In chemical bonding, again, we're going to start to bring in a lot of things we work together. In fact, with your atomic theory 2, last unit, the unit you finished up with, it's very, very beneficial as it sets the foundation as we move on to this chemical bonding. So let me fill in the actual points here, and you already have this from your notes. So we go back and it says, okay, what is a chemical bond? And a chemical bond is a force that holds atoms together. So why do atoms bond? Well, they do become more stable. That's the whole primary reason behind what we see on the periodic table and why things do what they do, is to the point of reaching stability. So maximum stability occurs when electrons have the same configuration as a noble gas. So there's two forces, however, since we know that the electrons are negative, so when the negative comes close to negative, there is a repulsion force that actually is taking place as these atoms come closer and closer together. However, when the attraction force is greater than the repulsion force, that's when a bond will actually form. Three types I want you to be aware of. Ionic, that's a transfer of electrons. Covalent is sharing of electrons. You should remember those back from biology. Metallic is a delocalized electrons. What I mean by that is basically the electrons have the freedom to move, and they can actually kind of move down the street to their neighbor's house and play with their neighbors down the street and come back. So they have the ability to move, and that the ability to move gives us a great idea about how metals can actually conduct electricity, because with their electrons being able to move, they can kind of pass electricity on through a piece of metal from one end to the other. Valence electrons. We already talked about this. You've dealt with this a lot of atomic theory. And those the valence electrons, by definition, are the outermost electrons, usually in the S and the P, the highest subshell, the highest shell for the S and the P. These are the electrons involved with bonding. Now, the transition of the elements sometimes in the D subshell, and we saw that actually in your atomic theory last time, so where the D can actually come into play. What they're looking for is they're looking for a full octet. They want the appearance of a valence electron. So that's where we have our octet rule. And that's why atoms tend to form bonds until they are surrounded by 8 valence electrons. Exceptions we have like helium. Helium or noble gas was our exception to our quote-unquote full octet. It has a maximum of 2. Lithium has 3 electrons, but a +1, it will lose 1, gets down to a appearance of a helium. And beryllium +2 has 4, but it loses 2, and it also gets down to an appearance of a helium as well. So those are some exceptions we're dealing with. Other than that, we're primarily looking for full octets. Ionic bonding. Let's focus first on ionic bonding. Ionic bonding, again, we have a transfer of electrons from a metal to a non-metal. And if you remember this back with nomenclature, we dealt with ionic compounds quite a lot when we dealt with the actual compounds we dealt with. So cations positive, anions negative. Positive because it's lost electrons, anions are negative because they've gained electrons. In the process of them reaching a point of stability, they have the appearance of a full octet. And so this positive and negative attraction forms what we call an electrostatic force. Great test question. Electrostatic force. Now, to get a good idea about this electrostatic force, we've already memorized cations and their positive charge, and anions, the negative charge. You know, group 1 is a +1, for example. Group 16 is going to be a -2. We know that, for example, but we're going to take a closer look at it, taking a look at what we call Lewis dot formula. The Lewis dot formula, we're looking at only the valence electrons. So sodium in group 1 has 1 valence electron. A sodium ion, meaning Na+, again, is just Na. We just show it as Na+. Has lost that valence electron. For a non-metal, though, it's slightly different. First of all, the Lewis dot formula looks the same, but fluorine's in group 17 has 7 valence electrons. But now when it becomes fluoride, we give it a full octet. We put brackets around it. We put its charge on the outside of the brackets, showing how many electrons it actually gained. So cations, you just put a positive, anions, you give them a full octet, and you put a charge on the outside of the bracket showing how many electrons they gain to acquire that full octet. Magnesium, for example, is in group 2, has 2 valence electrons. Magnesium ion is Mg2+. Oxygen, group 16, has 6 valence electrons. It wants to gain 2 to get a full octet, so it's going to say -2. So we put full octet, put brackets around it, and -2. Now, if we were to draw out these Lewis dot formulas with the actual compounds, we will do this a couple times, but after this, our primary focus will be on covalent. So I know sodium, if I look at the electron configurations, Here we see that again, that we see the sodium has 1 in an s orbital, has 1 valence electrons, where my chlorine has 2 in the s and 5 in the p, so it has 7, both in the third energy level. Realize again that the sodium wants to donate and the chlorine wants to gain, wants to become a p6, and the sodium wants to drop down back to a full octet with a 2s2, 2p6, and so they transfer electrons. Another way we can show it, we can show the dots, and we see the transfer of that electron takes place. To draw out the actual Lewis dot formula for an ionic compound, it's a Na plus, and then in brackets I put it at my chlorine with brackets at -1, meaning it gained 1 to get a full octet. Magnesium in group 2 has 2 valence electrons. Chlorine has 7 wants 1 more, so magnesium gives 1 to one of them and 1 to the other. So we already knew that magnesium is a +2, chlorine is a -1. We need 2 chlorides to zero it out. To actually show this, we'd actually do 2 plus in the middle, and on either side we put a chloride on either side to show the Lewis dot formula for an anionic compound. So a little more about ionic compounds. Again, they form a crystal lattice, and it's a 3D arrangement of positive and negative attractions to each other, and they form this 3D lattice. The structure, very, very strong structure, and we see this with sodium chloride. And we'll understand the angles of the actual salt we form here with our ionic compound, cation, anion, really depends upon the size of the cation and the anion, creating the different bond angles, therefore creating the different shapes of our crystal lattice. The lattice energy, we're going to have to be going into this. The lattice energy, by definition, is the energy absorbed when 1 mole of an ionic solid is separated into its ions. Understand this, lattice energy is always endothermic, means the energy is absorbed. Lattice energies are generally large values, which show that. Because of large values, we deal with lattice energies, deal with ionic compounds. They show that the ionic compounds are strong. They show that ionic compounds have, because they're strong, they have a high melting point. And because they're strong, we generally find them as solids at room temperature. The amount of energy when we deal with this lattice energy depends upon 2 things: the distance between the ions and the charges of the ions. Of the 2, charge takes precedence. Always look at charge first. If charges are the same, then you compare their distances. And this we're just going back to the periodic trends and seeing the actual size of the atoms. So we did measure this. We're a formula called Coulomb's law. The beauty about this is there's no math involved. It's just reasoning. So capital E is my energy. Lowercase k is Coulomb's constant. We're not doing any math. We don't worry about it. The Q1 and the Q2 are talking about the charges, and R is the radius, or the distance between the 2 atoms. So we're focused first on the Q's. If Q's don't answer our question, then we focus on the radius. The larger the Q, then in fact the larger the charge, larger the number, excuse me, not the charge, larger a number. So a +2 and a -2 have the same. It's basically you're measuring how far away from 0. The greater away from 0, whether it's a negative or positive, the greater the charge. So we compare compounds, for example, in letter A, want to compare the highest lattice energy. There's radius, for example, between the 2. But if I want to measure my highest lattice energy, I have calcium oxide and calcium sulfide. I see a calcium is +2. It's present in both of them. Oxygen and sulfur are both in the same group, column 16, so they're both -2. So in that situation, my charges don't answer the question, therefore I have to look at the size. And remember, as we move down a column, you get larger, so as sulfur gets larger, it moves further away from calcium, therefore it's weaker. And that's where we deal with the atomic radius in that situation. So again, we see the charges are the same. So again, remember, charges are the first thing you look at. If charges don't answer your question, then you look at the radius. Same charge. Again, but oxygen is smaller, therefore closer, we're therefore stronger. The next one, you have lithium hydride and calcium hydride. And this one, both of them have a hydride, which is a -1. Lithium is a +1. Calcium is a column 2. It's a +2. Therefore, I would say, oh, calcium is my winner, +2. 2 is, again, a greater number. So in that situation, calcium hydride is going to have a stronger lattice energy than my lithium hydride will. We look at the table up here and we ask, well, why is the order of lattice energies, why does it get lower and lower as we move down lithium fluoride, lithium chloride, lithium bromide, lithium iodide? Where we realize all lithiums are the same, but we're moving down our halogens, column 17. Remember, as you do move down a column, it gets larger. As it gets larger and larger and larger, it gets further and further away, therefore weaker and weaker and weaker. And that's why the lattice energy actually decreases in that process. Which has the higher energy, magnesium chloride or sodium chloride. Both have chloride. Chloride's a -1, but magnesium is +2, sodium is a +1, therefore +2 wins, larger number wins. And that's why it's such a, and so it's pretty straightforward. There's, not a whole lot, there's no math involved, it's just understanding your reasoning. Just understand larger number wins. That's, you always look at the charge first. Larger number wins, doesn't matter if it's positive or negative. After that, you look at the size, and that's where the periodic trend for atomic radius comes into play. So make sure you're familiar with that as well.